today's session I am going to explain the time analysis. So, in this subject control of mechatronic system, we are going to study the behavior of the different systems. So, in that the first one is the time analysis. In the today's session, the outcome is after completion of this session, you have to understand what is the time analysis. So, in this session these are the topics we are going to cover. One is the time response for the different systems, how the time response will be there, and standard test signals and relation between standard test signals, the Laplace transformation of test signals. So, these are the topics covered in this session. Now, let us see this in this time analysis, the time response of these control systems. So, the time response represents how the state of a dynamic system change in time when subjected to the particular input. At particular input, what is the state of the dynamic system that we are going to study with reference to the time. And since the models we have derived consist of differential equations, already we have seen in the last video. So, the different models, the developed the models, the mechanical, electrical. So, in those differential equations we developed and we studied the behavior of those systems, and the differential equations, some integration must be performed in order to determine the time response of the system. So, those differential equations we have to integrate it and we are getting the time response of the systems. For some simple systems, a closed form analytical solution may be available. However, for most systems, especially non-linear systems or those subjected to complicated input forces, this integration must be carried out numerically. So, most of the practical systems are non-linear systems, more complicated systems are there. So, those are we are going by using this numerically. You can solve these problems using the numerically. So, the time response in this in time domain analysis, we have going to discuss the time domain analysis and frequency domain analysis. In the time domain analysis, the response of a dynamic system to an input is expressed as a function of time. So, in this time domain analysis, the response of a dynamic system to an input is expressed as a function of time. So, it is possible to compute the time response of a system if the nature of input and the mathematical model of the system are known. Already you have discussed in the last video how to develop the mathematical models for the different the cases. Okay. So, you have to first develop the mathematical models, then we are going to the find out what is the response of that system in terms of the time. Those are concentrating as a time analysis. So, usually the input signals to the control systems are not known fully ahead of time. So, ahead of time those are not known, generally will go for this time analysis. Usually the input signals to the particular control system are not known fully ahead of time. So, those generally will go for the time analysis. And for example, in a radar tracking system, if we take the radar tracking system, the position and the speed of the target to be tracked may vary in a random fashion. Okay. If we take any target through this the radar system, it is very difficult to get that particular position. Okay. So, it is randomly varying. So, that is the best example of this the time analysis. In a radar tracking system, the position and the speed of the target, may vary in a random fashion. Okay. May vary in a random fashion. So, it is therefore difficult to express the actual input signals. It is very difficult to express the input signals mathematically by simple equations. Whatever the mathematical models we developed, the simple mathematical differential equations, those are not sufficient to analyze the response of these systems because of this random nature. So, what are the general test signals are using in the time analysis? We will see this the 4 test signals we are using. The characteristics of actual input signals are a sudden shock, a sudden change, constant velocity and constant acceleration. So, these are the four varieties of the test signals to that particular control systems are generally we are come across. One is the sudden shock, one is the sudden the change, one is the constant velocity and constant acceleration. So, the dynamic behavior of a system, is therefore judged and compared under application of standard test signals. These are the standard test signals that is a sudden shock or sudden change or constant velocity or constant accelerations. So, or a combination of these, an impulse, step, constant velocity and constant acceleration. Whether the signal is a impulse signal or whether signal is a step signal or whether signal is a constant velocity signals or the input signals are constant acceleration signals. According to that, we are going to analyze the time analysis of those systems. So, another standard signal of great importance is a sinusoidal signal. So, in addition to these four categories, what are the four categories? That is the impulse, step and constant velocity, constant acceleration. In addition to these four, so there is a sinusoidal signal also we are using the input signal to the control systems and we are analyzing the output parameters. So, now see that what are the standard test signals. So, the standard test signals are first one is impulse signal. Impulse, that meaning itself is given a sudden shock, that impulse signals. The impulse signal initiate the sudden shock characteristics of an actual input signal. If you see the characteristics of that parameter, it is a constant, suddenly it will the rise taking place, that is known as the sudden the shock taking place, that is a impulse test signals. Okay. Generally, it is representing in the mathematical model delta t is equal to A if t is equal to 0. If time is equal to 0, then delta t is equal to A, and if time is not equal to 0, then it is equal to 0, delta t is equal to 0. And if A is equal to 1, if A is equal to 1, the impulse signal is called as a unit impulse signal. If the amplitude A is equal to 1, then the signal is called as a unit impulse signal. Now, if you see that here the time is taking an x axis and delta t is taking on the y axis. Okay. The sudden impulse, so at if t is equal to 0, it suddenly the increases. Okay. Suddenly it is increases and remaining time period it is 0. So, that is indication of this, and the remaining time period 0 at t is equal to 0 and delta t is A. So, that is a sudden impulse taking place. So, those signals are called as a impulse signal. Generally, this for giving the control systems, this is one of the signal generally we come across. So, you see that here the graph, but test signals, the for impulse signal, how the signals are there, the impulse signal. Okay. If you see that here it is a 0 entire, here somewhere it is having some impulse. Okay. Somewhere here it is see that impulse takes place, here is impulse takes place and here impulse, but gradually it is reducing. Okay. So, there is a different cases we are going to study how the impulse signals are looks like. These are the few examples of impulse signals are there. Next, step signal. Instead of the sudden, it is a step, the amplitude some value it suddenly that increases and it maintains that magnitude, that is called as a step signal. The step signal they imitate the sudden change characteristic of a actual input signal. Okay. So, that is if u of t is equal to A at t is greater than or equal to 0, for other than the 0. So, for always it is having this value A. Okay. And at t is less than 0, this is 0, that will be representing in this graph. Okay. The time versus the signal. So, it suddenly increases and it will maintain the same magnitude throughout the time. At any time period, it is having the same magnitude. That type of signals I will call it as a step signal. That type of signal is called it as a step signal. So, if A is equal to 1, if A is equal to 1 and this step signal is also called as a unit step signal. the unit that indicates if the magnitude is equal to 1, and this signal is called as a unit step signal. Okay. So, this second signal, that is a step signal, is suddenly it will rise to that particular value, and till it maintain the same value throughout the time period. That those type of signals are called as a step signals. So, next, ramp signals. It is not suddenly increases, it is gradually increases. If you see that here, the gradually, if the time is increases, and gradually this magnitude of the signal is also increases. Okay. So, that is called as a ramp signal. It like a ramp, how this value is increasing like a ramp. The ramp signal imitate the constant velocity characteristic of actual input signals. Okay. It is having the constant velocity of the signals, or generally we are go for this the ramp signals. It is gradually increases. It is representing this equation R of t, that is equal to A into t. Okay. If the t is increases, the magnitude is also increases. So, it is a see, it is a continuously it is varying, continuously it is increasing. The t value is greater than or equal to 0, and if t is less than 0, this magnitude is 0. And here also, if A is equal to 1, the ramp signal is called it as a unit ramp signal. A is equal to 1, the ramp signal is called it as a unit ramp signal. If you see that here, ramp signal with slope A, ramp signal with slope A at different time periods. You can observe this diagram. At different times, at time 1, the magnitude is A. At time 2, the magnitude is 2A. At time 3, the magnitude is 3A. So, likewise, the signals are varying, then those are called as a ramp signal with a slope A. If you find out slope at any point, the slope is obtained magnitude A. So, then this is called as a ramp signal with a slope A. And see here, the unit ramp signal. At everywhere, if you take at any point, at 1 the magnitude is 1, at time t the magnitude is 2, at time 3 the magnitude is 3, then this signal is called as a unit ramp signal. Okay. So, for the ramp signals, we are the mathematical we are representing this R of t is equal to A into t if t is greater than or equal to 0, if t is less than 0, this magnitude is 0. Okay. From 0 it is moving. Okay. And in different ways you can express this ramp signals. It may be the constant particular slope, or it may be the unit the ramp signals. Okay. If A is equal to 1, then it is acting as a unit ramp signal. So, this is regarding the standard test signal of ramp signal. So, now coming to the parabolic signal. The parabolic signal. So, the parabolic signal that imitate the constant acceleration characteristics of actual input signal. So, for constant acceleration of the input signal are representing the parabolic in the nature. Okay. Now, if you see this diagram, the time is on the x axis and the output is the y axis, and it is the parabolic curve, it is increases according to the time, the value will be floating in a parabolic nature. Okay. And coming to this equation for this parabolic signal, okay, the P of t is equal to A t square by 2, P of t is equal to A t square by 2, and if t is greater than or equal to 0, and if it is 0, if t is less than 0. Here also for all the case, if magnitude is equal to 1, that comes to the units. So, the parabolic signal is called unit parabolic signal. Whenever the magnitude is reaches to the 1, then that signal is called as a unit parabolic signal, unit parabolic signal. Now, if you see parabolic signal with a slope A, similar to this the earlier case, that is a uniform velocity, okay, that is a ramp, that how the slope is constant. Here also parabolic signal with a slope A. If we take at different time intervals and find out what is the magnitude of the signal, okay, so then the value, the constant slope value is obtained. Okay. And also a unit parabolic signal, if A is equal to the 1, then the signal is a unit parabolic signal. Okay. So, these are the basic 4 types of signals. Okay. What are the 4 types of signals? That is a impulse signal, that is a sudden shock. The sudden shock, it will at particular point of time, the sudden shock takes place, and remaining time it is the 0 value, that is call it as a shock, that impulse signal. And the second one is a sudden change, the magnitude is suddenly changed. So, that is call it as the sudden change the signal. And second, next one is a uniform velocity, that is a ramp signals, and uniform acceleration, parabolic signals. These are the 4 varieties of test signals generally we come across for all these control systems. So, now see that next relation between standard test signals. Now, we have seen these 4 standard test signals. One is impulse, step, ramp and parabolic. Okay. So, now, what is the relations of these signals? So, from the impulse to the step, and from the step to the ramp, and ramp to the parabolic, or from parabolic to the ramp, or ramp to the step, or step to the impulse, what is the relation? Now, just now we have seen all the mathematical equations of all these 4 types of the signals. So, first signal is impulse signal. Impulse signals is representing delta of t is equal to a and g 0, a is at t is equal to 0 and remaining it is 0. Okay. And for step signals, u of t is equal to a and 0, if t is greater than or equal to 0, that value is a, and remaining t is less than 0, 0. And coming to the ramp signals, the r of t is equal to a t if t is greater than or equal to 0, and is equal to 0 if t is less than 0. So, for parabolic, it is representing p of t is equal to a t square by 2 at t is greater than or equal to 0, and remain t is less than 0, this value is 0. Then how we can write down the relations between these signals? Now, let us see this. So, from impulse to step, from impulse to step signals is now integrating the whatever the equation of the impulse, you are getting the step signal. You see, integrating this equation, then you are getting the step signal. And if integrating the step signal, you are getting the ramp signal. If integrating this ramp signal, you are getting the parabolic signal. Okay. So, integrating the impulse, you are getting the step signal, and integrating of the step signals, you are obtaining the ramp signal, and integrating the ramp signal, you are obtaining the parabolic signal. Okay. And in the similarly, from the parabolic to ramp, so you can differentiating this parabolic equation, then you are obtaining the ramp equation. Now, let us see. From this parabolic, if differentiating, you are obtaining the ramp signal. Similarly, from the ramp signal, you differentiating, you are obtaining the step signal. So, you are obtaining the step signal. Similarly, for the step signal, you are differentiating, then you are obtaining the impulse signals. Okay. So, this the relation between the standard test signals are you can obtain from one signal to the another signal. The relations are either integration or the differentiation. So, from integrating the impulse, you are getting the step, and from integrating the step, you are getting the ramp signal. From integrating the ramp, you are getting the parabolic, and differentiating the parabolic, you are obtaining the ramp signal, and differentiating the ramp signal, you are obtaining the step signal. Differentiating the step signal, you are obtaining the impulse signal. So, there is a relations between the impulse and step, ramp and parabolic. So, while solving the problematics, okay, it is very much helpful for doing all these relations. So, next, most of these solutions we are using the Laplace transformations. Okay. Now, see that for each signal how we can write the Laplace transformations. Now, for impulse you have to see in delta t is equal to a0, t is equal to 0 and t is not equal to 0. And then in the Laplace transformation of this equation is obtained delta of replacing t with s and is obtained a. Okay. So, for Laplace transformation of the impulse signal is a. The Laplace transformation of impulse signal is a. And for Laplace transformation of step test signal, so that is a by s. So, a Laplace transformation of u of t, that is u of s, that is a by S. You have to, these are the very much required for further you are modeling all the equations and solution of these different the equations. We require the Laplace transformations. Okay, you can easy to understand for impulse what is the Laplace transformation, that is A, and for step what is the Laplace transformation, that is A by S. And for ramp, the ramp, that general mathematical equation is R of t is equal to A t and 0, and t is greater than or equal to 0 and t is less than 0. So, the Laplace transformation of the ramp equation is obtained A by S square. And similarly, for parabolic, the Laplace transformation ordinary equation is P of t is equal to A t square by 2, and Laplace transformation is 2A by S 3. So, for the ramp, the Laplace transformation is A by S square, and for parabolic it is a 2A by S cube, 2A by S cube. So, for all the 4 test signals, the impulse signal, the Laplace transformation is A, and for sudden it is A by S, and here it is A by S square and 2A by S cube. So, for the 4 test signals, the Laplace transformations are A by S, A by S square, 2A by S cube. So, using these Laplace transformations, we are going to further develop the solutions. Okay. So, the time response of control systems. So, time response of dynamic system responds to an input expressed as a function of time. And if you see here the block diagram, okay, at different signals, the system, what are the inputs we are giving and what are the output we are getting, this that will be explained through this model. So, the time response of any system has a 2 components. We are going to analyze the time response of any system, either of these transient response or steady state response. What type of the response is there, based on that we are going to analyze. Basically, these time analysis are having these 2 responses, one is the transient response and steady state response. Now, see the time response of control system. So, when the response of the system is changed from rest or equilibrium, it takes some time to settle down. The transient response is the response of a system from rest or equilibrium to the steady state. So, the response of the system after the transient response is called the steady state response. Okay. If you see the signal of the control system, how the response is there, if initially it is having some transient, then it will come to the steady state, that will be representing in this graph. Okay. Now, if you take the step input signal, okay, and with respect to the time, what is the response is shown in this graph. Okay. From this point to this point is in the transient stage, and after that it will goes to the steady state stage. If you see that here, it is a transient response. This entire period is a transient response, because in this period the signal is varying, and from this almost it is a constant signal is obtained, that is comes under the steady state response. Okay. So, initially it is having some transient period, then it will enter into the steady state response. That will be, you can easy to explain with the help of this graph and the signal how it is varying. Okay. So, when the response of the system is changed from rest, because it is initially it is rest, to the equilibrium, it takes some time period, to settle down. So, that time period is in this case, this time period is 16 seconds. Within the 16 seconds, it will come to the steady state. From 0 to 16 seconds, it varying from 0 to 5. Okay. After that, it is almost it is having maintaining the 5 the output value. Okay. So, the transient response is the response of a system for rest or equilibrium to the steady state. So, the response of the system after the transient response is called as the steady state response. So, this is regarding this introduction to the time analysis. We have studied in this today's session the following 4 types of test signals. One is a impulse signal and step signal, ramp signal, parabolic signal, and how you can develop the Laplace transformation of those signals also we have seen. So, for the impulse signal we are representing the Laplace transformation is A, and for step signal the Laplace transformation is A by S, and for ramp signal the Laplace transformation is A by S square, and for parabolic the ramp signal is 2A by S cube. So, these Laplace transformations are required to further framing the different equations. Now, we can see that just list out what are the few test signals we come across known to you, and we can just study this behavior of the test signals. It is very much required for analyzing for carry out the time analysis of any control systems. Okay.